Hello, welcome to my AS Physics video on stress and strain. So, a stress causes a strain. Well, stress is a formulae which is tensile stress, and stress is the force over the cross-sectional area. Units are newtons per meter, or you could just simply call them a Pascal in pascals. So tensile, there's another way to define it. It can also be defined as a change in length, i.e. the extension. It's divided by the original length of the material. So this is just a number. No units. I hear you cry. No units. So it doesn't matter whether the force is producing stress and strain are tensile or compressive, the same equations apply. The only difference is that you tend to think of tensile forces as positive and compressive forces are negative. Now this is not true. Well, it is. We will prove it using this diagram. Well, shoddily drawn one. So this is the force F. Now, if you remember from the previous video, the extension brings about an equal and opposite force on both sides. So this is the extension E. Original length L. And the cross-sectional area A. So compressive forces is what is pushing the cylinder back to its original shape, and tensile forces are positive as they are the force applied, and the compressive forces are considered to be negative. So this is true because the two words mean tensile. You're putting tension onto it, and compressive means that you're squashing it. So yes, it is true. It's always nice to have a deriving diagram in order to prove it, so I will leave it up there for you to digest for a little bit. So a stress big enough to break the material is called the breaking stress, and the effect of the stress is to start to pull the atoms apart from one another, and the stress becomes so great that the atoms separate completely and the material breaks. And this is shown by point B on the graph. The stress at which this point occurs is called the breaking stress. The points marked UTS on the graph is called the ultimate tensile stress. This is when the maximum stress that the material can withstand happens. So a point marked UTS on the graph is called the ultimate tensile stress, which is this part here. And yeah, I've just explained it. It's the material that maximum stress that the material can withstand. And you can also store elastic strain energy, which is the energy stored in a stretched material. So before the elastic limit, all the work done in stretching is stored as potential energy in the material. This stored energy is called elastic strain energy. And on a graph of force against extension, the elastic strain energy is given by the area under the graph. I've just put X here for extension because I haven't got room to fit it in as I have such huge handwriting. So this triangle is the value of the elastic strain energy. In order to find that, you just do half times A times B for the area of a triangle. So then you'd use the X intercept, Y intercept, and then you'd calculate the triangle like that. So we can also calculate the energy stored in a stretched wire. So the work done on the wire in stretching it is equal to the energy stored. So work done is equal to force times displacement. And however, the force on the material isn't constant, it rises from 0 up to force F. So to calculate the work done, we use the average force between 0 and F. So the first equation is work done equals half times F times E. Squeeze a multiplication sign in there. So the elastic strain energy E is called half Fe, or you can put half times Fe in there as well, but since this is an algebraic expression, just like the work done one, I will put half times F times E. But you must remember, in algebra, when the two letters are next to each other, you multiply them. But since you're looking at this video, you probably already know that by now anyway. No need for me to tell you again. If we also look at, because Hooke's law has been obeyed, F is equal to K, we can also substitute the value of F equals Ke into this final one, E equals half Ke squared. And as the material is stretched beyond the elastic limit, some work is done in separating the atoms, and it's not stored as strain energy, and it isn't available when the force is released. So if we look at a question now, 3 questions. A steel wire is 2 meters long. When a 30 Newton force is applied to the wire, it stretches 4 millimeters rather. The wire has a circular cross section with a diameter of 1 millimeter. So what is the cross-sectional area of the wire? We need to calculate the tensile stress in the wire and the tensile strain of the wire. Question number 2. A copper wire which obeys Hooke's law is stretched by 3 millimeters when a force of 50 newtons is applied. So we need to calculate the stiffness constant for this wire in Newton meters, or Nm minus 1. So what is the value of the elastic strain energy in the stretched wire? So for question 3, a pinball machine contains a spring which is used to fire a small 12-gram metal ball to start the game. The spring has a stiffness constant of 40.8 Newton Nm minus 1. It is compressed by 5 centimeters and is then released to fire the ball. So is it A? The maximum possible speed of the ball is either A 1.86 ms minus 1, 2.92, 4.12, or 8.5 ms minus 1. So I'll give you a quick 5-second pause and we'll have a look at the answers. Okay, hopefully you paused the video and had a go at the questions and you're ready to check the answers. So for part 1, the area is pi d squared, or pi r squared is commonly used. So if we use either one of the two, we will get the cross-sectional area to be 7.85 times 10 to the minus 7 meters squared. Now the stress, it's force over area, so we put 300 newtons over 7.85 times 10 to the minus 7, which is equal to 3.82 times 10 to the 8 Nm minus 2. Okay, so for part C, strain is extension over length, so 4 times 10 to the minus 3 over 2 is 2 times 10 to the minus 3, and that is 1 mark. And for question 2, F is equal to Ke and K equals F over E. So K is 50 divided by 3 times 10 to the minus 3, which is equal to 1.67 times 10 to the 4 Nm minus 1. And for part B, elastic strain energy is half times Fe, and given the elastic strain energy is half times 50 times 3 times 10 to the minus 3, that is 7.5 times 10 to the minus 2 joules. So we're going on to question 3 now. E equals half Ke squared. Half times 40.8 times 0.05 squared is equal to 0.051 joules. So the energy, kinetic energy, is equal to E, which is equal to half mv squared. So V squared can equal 2 times E times m, or divided by m rather. So V squared is equal to 2 times 0.051 all over 0.012, and that's equal to 8.5. So V is 2.92 ms minus 1. So the answer is B, 2.92 ms minus 1. Okay, so I hope you found this tutorial useful. Please like, comment, subscribe, or whatever you YouTubers do. And until the next time, thank you for watching and goodbye.